You ever wonder how your phone seems to know exactly what you're going to type next? Or how some systems can predict the wild swings of the stock market? Well, the secret to all of it, the common thread, is sequence. For the longest time, teaching a computer to understand that one thing follows another was a massive, massive challenge. Today, we're diving deep into recurrent neural networks, or RNNs, to see how we finally gave machines a memory. So just think about it for a second. If I start a sentence like, "The quick brown fox jumps over the lazy," you almost instinctively know the next word is dog. It's second nature to us. But for a computer, that's been an incredibly tough nut to crack. What are they missing that we just get? Well, the biggest hangup has always been with traditional neural networks. See, they look at all the data at once, kind of like taking a single photograph. To them, the words dog bites man and man bites dog are just a jumble of the same three words. But as we all know, the order changes the meaning completely. When it comes to sequences, order isn't just important, it's the whole story. And this is exactly why those standard networks just fall flat. They've got such limited context. It's like trying to understand a whole movie by looking at a single random frame. They can't handle inputs of different lengths, which is a huge problem for things like sentences or music. And if a pattern shifts just a little bit over time, they get totally thrown off. We needed a new kind of architecture, one that was built from the ground up to remember. And that brings us to the hero of our story, the Recurrent Neural Network, or RNN for short. This is a special kind of network designed specifically to handle ordered data, and its defining feature, the thing that makes all the difference, is a feedback loop. This little loop allows information to stick around, creating for the first time a genuine form of memory. This feedback loop is the absolute superpower. It's the secret sauce. Think of it like a short-term memory for the network. Instead of just seeing one word and immediately forgetting it, the RNN can hold on to what it just processed and use that context to understand the next thing it sees. It's like the network is finally reading a book and actually keeping track of the plot. So, how does this actually work? Let's break it down with the phrase, "I am." First, as you see in step 1, the network processes the word I. It then creates a little summary of what it just saw. That's the hidden state in step 2. Then, and this is the magic part, it takes that memory and feeds it back into itself along with the next word, am. This whole process repeats, so with every new word, the network's memory of the context gets richer and richer. But just having a memory isn't the whole story. You have to teach the network what's important to remember and what's just noise it can forget. This is done through a process called backpropagation through time. It's kind of like a teacher going back through the network's homework, step by step, and giving it feedback to help it improve its memory for the next time around. Now, when you try to train these networks, you run into two classic villains: vanishing and exploding gradients. Think of vanishing gradients as a form of amnesia. The memory of events from way in the past gets weaker and weaker with each step, until poof, it's just gone. Exploding gradients are the exact opposite. It's like the network is overreacting, where one tiny event in the past creates this massive, destabilizing snowball effect on the present. And just look at this number to see how quickly that amnesia can kick in. If you take a value like 0.9, representing the strength of a memory, and you multiply it by itself just 100 times, say for a sentence that's 100 words long, you end up with this, a number so incredibly small it's basically zero. That's how fast the memory of the past can completely vanish. And here's the crazy paradox. The very thing that causes these problems is also the RNN's greatest strength, weight sharing. The fact that it reuses the exact same set of rules at every single step is what allows it to handle sequences of any length. But it's also why you get these gradient problems, because you're just multiplying by the same numbers over and over and over again. All right, enough with the theory and the challenges. Let's see how one of these incredible tools actually works in the real world. We're going to walk through a case study on forecasting book sales. The big question is, can an RNN look at a history of sales data and give us a truly accurate prediction of what's going to happen next? Okay, so first things first, we've got to get our data organized in a way the RNN can understand. Now, this table might look a bit technical, but just think of it like setting up a special kind of spreadsheet. You have one dimension for each book, another for the time step, like months of sales history, and a third for the actual sales numbers. This structure is absolutely crucial because it puts everything in perfect chronological order, which is exactly what the RNN needs. And after all that training, how'd we do? Well, check this out. The training error, that first bar, is incredibly low. But what's even more important is the testing error on the right. That's how the model performed on data it had never seen before. And look how close those two numbers are. That is a fantastic sign. It means our model didn't just memorize the past, it genuinely learned the patterns. So, what does an error rate like that actually mean in the real world? It means our model's predictions are, on average, only off by about 2 to 3%. And for a book publisher, that's not just a cool statistic, that's a complete game changer. That level of accuracy helps them decide exactly how many books to print, so they're not wasting money on overstock or missing out on potential sales. It turns forecasting from a wild guess into a real strategic advantage. Now, I have to stop here and share the absolute number one golden rule when you're working with time series data. And this quote says it all. You can never shuffle your data. Why? Because if you do, you're accidentally letting the model peek at the future while it's training. It's like giving a student the answer key before the test. You always train the model on the past and test it on the future. End of story. So, here we are. We've given machines the ability to remember, to learn from history, and make predictions about what's next. And this technology is reshaping our world. It really leaves us with one massive, thought-provoking question. Now that they can learn from our past, what are the stories, what are the sequences that are so important that we can't ever let them forget?